Hi, in this lecture I'm going to be covering the OSI network layer, and if you're following in the textbook it happens to be chapter 5. Alright, so I'm going to discuss the importance of the network layer. I'm going to explain why it's important in connecting devices together, or how devices are able to communicate with each other using addresses. So this means we're going to talk about IP addresses, we're going to talk about a concept called connection lists and best effort. I'm also going to explain to you how these addresses can be divided, and network devices can be divided into networks. All right, so let's go straight in, and I have a diagram here, and I'm going to use this diagram to just discuss a few concepts. The first concept is, in order for this man over here to communicate with his colleague over here, you can see that she is in a different geographic location. You see here there's a cloud, so we can call that the internet, and he may be in one country or city and she may be in a different country or city. In order for him to communicate with her or her to communicate with him, they would need to know each other's address. In the same way as if you are going to visit your friend, you need to know their unique address. And the reason why I say unique is no two addresses can be exactly the same. Otherwise, that would be referring to the same place. So, for example, if this man was residing in Main Street in a town in Kansas, and this was in the United States, and she was in Johannesburg, also in Main Street. Already we see that the streets have the same name, but they happen to be in different countries. So this is kind of a metaphoric example, just explain to you in terms of IP addresses and how the different IP addresses can allow us to see different groupings. For example, there might be thousands of people living here in Johannesburg, so they all live in the same city, but their individual house number, maybe she lives in house number 25 Main Street, Doornfontein, Johannesburg. So you can see there was the city and the suburb and then the street and then the house number. So this makes it unique. And if that doesn't make sense, you'll see as we go along how the IP addressing is very important in order for us to communicate in a way addressing the network. So we're providing her with an address, him with an address, and all the devices in the middle also need unique addresses so that these datagrams or these packets, because now we're on the layer 3, we'll talk about packets, can get through the network. So what happens is the layer 3 is very important in addressing, and the minute we provide a device, there's a computer with an address, we now call it a host. And a device needs to have a unique address. And the process takes place on layer 3, and this is why we often call it addressing the network. Now, if you're a network engineer, you'll spend a lot of time on layer 3 because this is also the layer where routing takes place. Now, in order for us to direct the packets to their destination, we need to have something called a source and destination address. For example, in order for this man to send the packet, his data, there's his data, he might be using an email client, and this client is sitting over here. Why I'm putting it here? Because the software, maybe he's using Outlook or even a web browser, whatever he's using in terms of his email client or his login, it will be sitting on top of the application layer, dealing with the application layer, and then his data will be prepared and it will go down to the transport layer. And I do have a video explaining the exact details of the transport layer. The transport layer is going to provide the port numbers and make sure that the individual conversation remains independent and unique. So that's where the transport layer is going to come and put something called a port number. But now a port number and a source and address are two different things. For example, we'll look in the Wireshark software and I'll show you port numbers, and I'll do that right now. I have Wireshark loaded and I'm going to just quickly go here and I'm just going to look for, let's just play this. This is Wireshark, and I'm just going to quickly look for a TCP packet here. There we go. And if you look in Wireshark, you will see we have 4 layers. Now I'm on layer 4, And can you see straight away, I see source port and destination port. So you can see that the transport layer has a lot to do with the ports that are assigned to the datagram. So you can see there is the source port and destination port. But now in this lecture, we are going to be busy with the layer 3. And this is the layer of IP. So what do you notice when I open layer 3 of Packet Tracer? Now, if you're not sure what Packet Tracer is software that allows you to view inside the packets that are leaving and coming to and from your computer. So this is a packet that I'm viewing. It's almost like opening up the network card and looking inside. That's what Wireshark is doing. It's looking at the packets. And I've opened up this one packet. And can you see that immediately on layer 3, you see layer 1, 2, 3, suddenly there comes IP addresses. There's an IP address, 10.00.20, and the destination happens to be 91.225.248.123. But if I go a layer higher, which is the transport layer, can you see that there are no IP addresses there? See, the layer 4 has nothing to do with addressing the network. Layer 4 has other features, as I described in my transport layer lecture, and it's to do with making sure the packets, the segments arrive, making sure that the data rates are correct. For example, that it sends and receives enough segments in a certain time frame, and also the protocol. Is it sending it via TCP or UDP? So that's very important in terms of dealing with your software. For example, here I have a Mozilla open, and I can open several windows here, and maybe I want to go to News 24, maybe I want to go to Facebook. So there I've got two different tabs open. It's the transport layer that is going to allow us to send the individual data into this tab and the individual data into this tab, but has nothing really to do with the IP addressing. So the transport layer has to do with the ports, and the port is assigned or put onto the segment, and it then moves down from the transport layer and it goes to the network layer. So the segment is all ready for transmission. It is prepared. It's got the port numbers. The transport layer will be able to track it and know that the one segment is going to Mozilla Firefox, the other segment is going to Outlook, and the other segment maybe is going to just do a Windows update, and the other segment might be to do with another tab in a web browser. So the transport layer is going to track all those individual conversations. Listen to what I'm saying. It'll track the individual conversations. Now, all those data segments are ready to be sent. Now look at this. It gets sent, the segment shifts through to the network layer, and now it needs to be addressed because we need to now get it to the segment to these people on the network. So now we need to address the network, and that's where we come to the IP addresses. We need to attach IP addresses to our segment, and that is why I showed you this Wireshark little window here. If we go to layer 3, we can see that IP addresses are put here. And while I've got this open, I just want to lay a little foundation here, or get some seeds planted here. Just look at these words: version, header length. We got service field, total length, identification, flags, TTL, time to live, the protocol. We've got checksum. And then there's the source and destination address. Now, why did I just say that? And I did that because a little bit later, I'm going to show you the protocol header. This is the header of an IP version 4 packet. So this is what's in front, or what's encapsulated or put as labels in front of the segment. And I don't know if you heard me. I said version, header length. There was packet length. There's some other features here, fragment offset. Okay, then there's time to live. Remember, I said protocol, source address, destination address. So can you see all these labels that need to be attached as a header in the front of the data? There's the data, Maybe that data was you're sending her a message and you're saying, hey, how are you? There's the data. Maybe it's just the first word called hey. It needs an IP address, because where is this hey or hello going to? Well, it needs an IP address, and that's going to happen on the network layer. We're going to put an IP address because the this device needs to be able to connect, and I'm using the word connect a bit loosely because he's not really connected. He's not plugged in to his colleague. And that is why we call it connectionless. He doesn't have a direct connection to his colleague. You can see that there are a total a cluster here of routers. And you might find that maybe he sent 3 little words. Hey, how are you? So that was the hey, how are you? So that's 4 little communication pieces. So the hey might go via that route, and the how might go via this route, and the R might go via that route, and the U might go via a totally different route. And that is why we call it connectionless, because it doesn't the network layer doesn't require it to have a constant almost like a hardwired connection. No, it can route the different packets ad hoc. And I say the word ad hoc because it depends on the loading of all these interconnected devices. All right, now this is still the introduction, and I am going to go through this step by step. So you can see that routing is very important on a very important protocol in this layer. So the network layer must provide services to direct these packets to their destination host. The source and the destination hosts are not always connected to the same network. She's not on his network. She's on a totally different network, maybe in a different geographic location. A packet may have to travel through many different networks, as you can see. And along the way, each packet must be guided through the network to reach its final destination. And then look at all these intermediary devices. These are intermediary devices, all these routers which connect the networks, and these routers provide us with this ability to communicate across networks or geographic location. So what is the role of the router? The role of the router is to select paths for direct packets to their destination. So this router will determine, based on status updates from other routers, whether it's going to forward the packet in this direction or maybe a different direction. It might send it via this direction. And the next packet that's arrived here, this router may say, well, hang on, this route is now too overloaded, looking at the metric, and then it will now forward it to this router. This router will then look at its routes available and say, okay, I know where I can send this packet. I must send it via this router, and so forth. So you can see how the routers are making these moment by moment decisions, and that's based on quite a lot of factors, which I will explain, but in other lectures. I have the lectures on the routing protocols. All right, now what happens is, as the data arrives at this lady here, we will need to decapsulate. And decapsulation means to slowly unpack all the headers. You see, there was the data, and then there's the header. So there's the data, and there's the header. But each layer has its own header system. So what happens through decapsulation is each layer goes and looks for its own header. So the layer to do with IP addresses will find IP addressing and time to live and routing information in the header. The layer to do with the transport layer will find port addressing and sequence numbers in order to put the data in the right order once it has arrived. So you can see how these headers are built up once the data is ready to be sent, and it is broken down once it arrives at the receiver, as she then her OSI model OSI layers will eventually break down the entire frame, then it'll go to a packet, then it'll go to a segment, a datagram and segment, and then it will find itself as just data. Okay, so we've covered the decapsulation, and now let's maybe look at some animation just to highlight this point that I'm trying to bring across. There we go. The host, he wants to send a message to his colleague who's in a different geographic location. There's the data. Maybe that's the word hi. Can you see it is encapsulated? We're putting the transport layer features there. This will have, now if you want to know what is going to be there, I'm going to show you. Transport layer, layer 4, we are going to attach port number, source port. It's going to have a destination port, the sequence number. Sequence number, it will tell the receiver the number assigned to that packet. It doesn't have to start at 1. I know you're seeing a 1 there, but it rarely starts at 1. It could be 100. And then we can see other fields here also in terms of putting these packets, these segments back in the right order. Flags, window size telling us how much data can be sent in one go, because it tests the bandwidth of the network, and then it just determines how much how many segments can be sent in one go. Window size, you see the checksum and timestamps and things like that. All right, so this is all the header information that is going to be put here. So if we reverse a little bit here, let's see if we can reverse that. Can you see there? That is what we've just put on to the data. You see, that's what I'm showing you now. Now it is ready. It's got the port number, the transport layer. It knows the individual conversation it is having. It knows which version or which software or application will be using that data. It might be a Microsoft Excel spreadsheet. It might be a PowerPoint. It might be a Outlook file. It knows it. It will track that conversation. And now look, the transport layer allows this segment to move down to the network layer. And at the network layer, it gets encapsulated once again. What are we putting on this segment in the network layer? Right, do I open this one? No, we've already done that. That was layer 4. Now we're going down a layer. I know this is now in the reverse order, because here, as you can see, we're going top to bottom. But in Wireshark, we're going bottom to top. So we see here, this is 4, 3, 2, 1, while this is 4, 3, 2, 1. So just account for that they are reverse ordered here. Now, we are now at layer 3, which is the network layer. And we are going to be using the IP address. Look there, version number, header length, identification, time to live, this protocol, checksum. This is a hashing that we allow to maybe check if there were any errors in the data in the entire packet on the receiving side. So it's like a sum. It's almost like if you've got a sequence of bits and then you multiply it by another sequence of bits, it should give you an answer. If you get this the right answer, well, then the checksum is correct. So this is just for error checking. And there's the source and the destination address. I'm not going to go into too much detail on all the labels here, because that will really take quite a lot of time. What I am going to focus is on the specific things in order to get the packet to the destination. That is the source address and destination. What is a source address? This is your IP address. Where do you find your IP address? No problem. It is sitting here in your network settings here. You can go to your network settings and you can go to your adapter, and you'll find these. Now you can see I have 2 Ethernet connections and 1 Wi-Fi. It doesn't matter. Whichever one is connected. At the moment, I only have this one connected, and you can see that I'll probably have an IP address here, and it's set by a router, so it's not assigned here, but I could assign it if I wanted to, That's my IP address. So that's the source IP address. And if you are not sure what your IP address is, you can easily just go and check it by pressing CMD and you say IP config, and you should get your IP address. There it is, 10.0.0.20. That is my IP address. And did you notice that that is the same IP address that Wireshark has picked up? You see, it says source. So this, I'm the sender, I'm the source. 10.0.0.20. And who am I sending to? I'm sending to somebody or some server on a network with their IP address called 91.225.248.129. The destination address is not my address. It is the address that I am attempting to send a communication, or I'm attempting to communicate with or send my data to. Right, so let's move on. Can you see there is the segment? The segment consists of the data plus all the headers of the layers that are above the network layer. So there we go. You can see transport layers header is already in there. And now we've put the IP address and all those layer 3 labels. And now we call it a packet. And I know I may be a bit loose with the terms, but I just want to highlight once again. Layer 4, we call it a segment. Layer 3, we call it a packet. Layer 2, we call it a frame. Layer 1, we call it bits. That is the literally ones and zeros, or the signal. It's the signal data. It could even be in an analog format across a network, but 99% of the time it is digital. All right, so this is layer 3. It is now encapsulated data. It's got the IP addresses. It now knows where to go. It knows where to go because the next hop, the next router will look at this layer 3 data, and it will make a decision based on its own routing table. And I'll tell you what a routing table is shortly. And it'll say, right, I know where this address is because here it says 192.168.36-5.5. So the router is going to attempt to locate this host via all these interconnected or intermediary devices. Right, so let's continue with the animation. There we go. Encapsulated one more time. You are welcome to watch my layer 2 video, which is dealing with Ethernet. And now what happens is MAC addresses are attached to this packet to be called a frame now. See, let me just show you the Wireshark. Now, although this is not part of this chapter, this is layer 2. Can you see now it says Ethernet? Ethernet is a layer 2 protocol. That is why it says Ethernet. And can you see that now we are dealing with MAC addresses? That is not an IP address. This is a MAC address. And you can see that it happens to be going to some Y-way device because it's picked up these hexadecimal labels here, 84.9FB5 hexadecimal address, and it's picked it up as a Y-way product. Then the source happens to be gigabyte, so it's picked up the model or the manufacturer of the motherboard because it happens to be a gigabyte Ethernet card. There we go, which is built into the motherboard. It's embedded. It's not a discrete graphic network card. So it's picked up the motherboard manufacturer because the network, the NIC, the network interface card, is on the motherboard built in. So you can see this is layer 2 stuff. So layer 2 has also got its own header. And then there we go. Look at that. Gets converted into signals, ones and zeros, goes through the network. Now we are coming to that lady, the colleague on the other, in another geographic location, for example. And look, this is the OSI model on her device. And her device will now deal with all this binary data, and as this data goes up the network, it will now decapsulate. So let's learn the language here. As it goes down the OSI model, encapsulate, because you encapsulate, you're adding. Now we're coming to this side of the network. We want to get the data out of this entire bit stream. So now we are removing headers. So we're calling it decapsulation. Look, there's the frame. We're going to remove this header. There is some footer data there. Decapsulating. And there we go. the transport layer is going to now know which port is linked to which conversation. And then the data will be useful, and the colleague will be able to get the message, and maybe that message was, hey. And the next message coming afterwards is, how are you? All right, so let's move on now. The network layer, in summary, is the layer that deals with the Internet Protocol version 4, and we're now well into the usage of version 6. There are other network protocols, not as popular. I'm not going to talk about those. I'm only talking about IP version 4 and IP version 6. I do have lectures on the IP version 6 and how to address and use these IP version 6 this IP version 6 protocol, but it's out of the scope of this lecture. We're going to focus on the IP version 4. All right, so let's move on. If you look at this diagram here, you can see once again that we've got a segment. This is the TCP IP. Do you notice the word here, TCP IP? They do work together. The TCP, the transport layer, deals with the segment. And then what happens is it sends it down to layer 3 to get an IP packet. So TCP segments are encapsulated into IP packets, therefore TCP IP. And then it becomes connectionless. Why is it called connectionless? Because we do not look for a connection before sending the packet. I don't know if you noticed on the diagram I had before, when this person wanted to send a message to his colleague on the other network, he did not first check if there was a physical connection. He literally just had her IP address or her address, and he got ready to send the data. So we call this connectionless. No connection is established before sending the data packets. But I want you to understand something. We are on layer 3. A connection is established on layer 4. So let's not get confused here, because layer 3 doesn't care whether there's a connection or not. Layer 4 cares. You see, it's a different responsibility. Whether there's a connection or not, or whether the receiver is available to receive the packet or has received the packet, falls on the shoulders of layer 4. It has nothing to do with layer 3. Layer 3's job is simply to address the network and send the packets, label them, and get them routed. Whether they get there or not, well, that's the job of layer 4. Layer 4 will decide what to do if the packets were not received, while layer 3's job is to route. Okay, so let's move ahead. So here we see it's connectionless, and then it says it's based on something called a best effort approach. So no overhead is used to guarantee packet delivery. Notice that when I showed you that header in the Wireshark, I don't know if you noticed, if you look at layer 3, do you see any numbering here in order to determine if the packet got sent or received? No. IP doesn't care. TCP cares. You see there it says sequence number, acknowledgement number. So TCP is in charge of whether the packet got received or not, and in which order it got received. So in terms of IP, in terms of layer 3 does not care. It doesn't even have fields for that option. So that's why we call it unreliable. Its job is to send and receive. If it sent it and the person never received it, IP doesn't care. TCP cares. The layer above will deal with that. Okay, another feature is its media independence. What does that mean? This is a beautiful feature of IP, and I'd like to see a diagram here showing you. Can you see that when we send information across a network, we might be connected via copper, maybe it's Ethernet. We might be connected via fiber optic, glass. We might be connected through a serial cable. Maybe we're using ADSL. Different cable, different protocol. But guess what? The IP packet can still traverse the network. Maybe we are going wireless. Yes, you might be using your wire. In many people's homes and even offices, they've reverted to wireless. And for me, I can't stand that because it's fraught with so many issues. But wireless is a viable protocol, and it is governed by the IEEE standards. And you can go and have a look at the BN, the N, and so on, the A, and the B standards, and the different frequency bands and so forth. But the point is, IP can still traverse an air network. And I call it air because it's over the air. You see, here we're going over copper. Although a lot of Cat5 cable is cladded, it's just got like a bronze dip or copper dip, but inside it's aluminium. You've got to be very careful when you're buying copper cable these days. Then we might be going over serial cable. Might even be an older protocol. Maybe it's frame relay. It's an old protocol. Now we're going optical fiber. Now maybe we're using a passive optical network. Maybe it's fiber to your home, fiber to the curb. All right. And then we come here, wireless. We might even have a satellite uplink. The point is that IP can deal with many different media formats. So IP is very resilient. It is probably one of the most resilient protocols available, and that is why it is so popular. All right, so what does this mean when we say it is connectionless? When you post a letter to someone, you write their address on the back of the letter and you post it. Do you know whether the letter was received or not? You don't. Unless the person phones you and tells you, you don't know. You send a letter in the post, boom, there it goes. The post office personnel will deliver the letter, hopefully, and this person may or may not receive it. You may not even know that you won't know that they receive it, and you won't know if they didn't receive it. And this is why it's called connectionless. And also, a very important feature is when you write the letter, you do not know the route that letter is going to take along its path to the person you're sending it to. Isn't that true? When you write a letter to someone, you may know their address. 41 Billignoot Street, Orange Farm, Orange Free State, South Africa. Great, you know that address, and you could literally GPS it and even see the Google view, the street view of the receiver. But which route is that letter going to take through the whole postal system? You do not know. And also, the postal service might decide that ad hoc, meaning they might decide, okay, today Johannes is going to take that letter via this route. Tomorrow, Tabor is taking the letters and he is going to start in a different suburb, and therefore he may take a completely different route through the suburb of Orange Farm, for example. So that is why I'm saying to you it is connectionless. But does the packet get received? Don't just say yes. We don't know. You see, that is the job of a different layer. Layer 4 will determine if it's received or not. Layer 3 does not know whether it is received. So that's why I said, does the packet get received? We do not know. It's not our responsibility to know if the packet got received or not. Okay, and remember that you might find that the postal service drop off the packet right here at the host, and just before the owner of this house comes to read the packet, a gust of wind comes and blows this packet, the letter away. So even though the postal service did do their job, the receiver still did not receive it. In the same way that somebody, the routers may have forwarded the packets all along the network correctly, but that person unplugged their device or went offline just before it could have been received. So this is one of the reasons why we call it connectionless. All right. Now, when I said earlier, it takes a best effort and it's unreliable and it's connectionless, I did allude to this different path system. For example, we might send a packet, as I said, we may send a sequence of communication called, "Hey, how are you?" So there's the first one, that is the hey. This is the second one, how, and this is the third one, are, and this is the fourth one, you. Right, so here we've got packet 1, getting ready, it's queued up, there it's at the router, and look at the route it took. Boom. He got it. Hey. Now what happens is you're sending packet number 2, and there goes packet number 2, and the network is suddenly very busy. And the packet went there, it went there, it went there, it went there, then it went back, then it went there, then it went there, then it went there, then it went there. Too many hops, packet died, never got there. So we never got this. Never got received. But he will not know. Layer 3 means that this sender will not know. And then they send packet 3, there we go, packet 3, and guess what? Packet 3 got there, and then packet 4 was sent, and it got lost along the way. So the receiver only gets 2 packets out of 4. What happens then? Well, IP does not know it. IP does not guarantee the packets will be received. Because it is connectionless, IP cannot account for what will happen by this router. So once the packet is sitting here, this router here will take responsibility for the packets that are sitting on its network, right? Fine. But it cannot guarantee what will happen in the future. So that is why it cannot guarantee whether the packets get sent. So even when packets are lost, it's not the responsibility of IP to solve it. IP's job is to route it, and route it quickly. And sometimes things get lost. And that is the point of the layer 4. Layer 4 will deal with all the problems that have happened with layer 3. So layer 3 is routing, preparing the packet with a correct addressing, encapsulate, decapsulate, and addressing the network. Whether the packet got there or not, this is the problem of layer 4. So I'm keep trying to differentiate for you the difference between layer 4 and layer 3. All right, so let's move on. Right, getting back to the header. Right, now earlier I said that we put the header, attaching it to the data. Now we call this a protocol data unit. Now I'm going to step through this little animation here, and it says the transport layer adds a header so segments can be accounted for and reordered at the destination. So this is the transport layer header. Now what happens is once it goes down to the network layer adds a header so packets can be routed through complex networks and reach their destination. Can you see that once we take the segment from the layer 4 and add another header, the new header does not interfere with the preceding layer's header or labeling information. So it's literally putting a sock on, and then you're putting a shoe on. The shoe does not interfere with the sock. You get what I'm saying? So it's not like this IP header does anything to the layer 4 header information. And that's the beauty of this thing, is that the routers on the network will be able to look only here at this IP header. And I'll show you what it does. I wonder if you can see. Yeah, it's a serial bit. It's a serial form of communication. You see, there come the bits. 1, 2, 3, 4, 5, 6, 7. The router knows to count the bits and see, okay, this part here represents a certain a field. For example, let's go back to the header. This is the IP version 4 header. So this is the header which is sitting over here. So if you're looking on the OSI model, would be over here. This header, the headers for the network layer, would be all this stuff over here. The version number, the type of service, the packet length, the fragment offset. And remember, I showed you this in the Wireshark. You see there, layer 3, not layer 4, layer 3. All that stuff, that's the header. And the router can deal with it because what it does is it knows, okay, byte 1 consists of version number and header length. Byte 2 is going to tell you whether it's high priority information or not. It gives, it enables the router to determine, if it should prioritize the packet or not. Then the packet length, and you can see it says there byte 1, byte 2, byte 3. So what is happening is the data arrives in a serial format like this, and there will be the first byte, and then the second byte, and the third byte. So the data comes in a serial format, and a lot of students don't understand this diagram. They think the data comes in like this, almost in this stacked parallel format, but it doesn't. You've got to think of it in terms of a snake. Like that. And then source address, options, padding. Okay, so what are all these fields? Now, I did go through them slightly, but I'd like to just go through in a little bit more detail. If you see here, it's got TTL. This is the number of hops before a packet is dropped. Each time the packet goes through a router, it gets decremented. So if you look at the Wireshark data, there should be a TTL. There it says 128. Every time this packet goes through the router, it gets decremented. Decremented means decreased. So the first router, this is quite high for a TTL. Usually it's about 16 or somewhere there. So let's just say, okay, 128. Then the next router will be 127. The next one will be 126. The next one will be 125. But this is quite high. This is not that common. So this is the time to live. And the reason why it gets decremented is because if a, let's get the diagram up here. Here we got this, this little diagram here. If the packet does not get to the end, and it just goes through this little interconnected network here infinitely, don't you think it's going to start loading up these resources? I mean, imagine there are millions of packets that just don't get sent to their destination, and they just keep getting, sent around the network. It's got to come to an end at some point, and that's what the TTL is. So if the packet does not find its way out of the final router to the destination, it will just keep on going round this network, and eventually there will be other packets as well, and it will really overload the resources. So what happens is we decrement this number, and when it gets to 1, then it gets to 0, then the following router will not forward the packet any longer. It blocks the packet once that TTL is completely decremented. Right, so that's the TTL. Then the protocol, well, this is very important. We need to tell the router what type of protocol it's using. Now there it says TCP. TCP is 6. And there are other protocols as well, like it could be ICMP, which will be 01. So using a numbering system, you can see that UDP is 17. So if you have a 17 here in this field, you're telling the OSI model, listen, the OSI layers, listen, I'm UDP data. So this allows the intermediary devices to know what the protocol is. And then there's the checksum, and there's the source address. This is your IP address, and then the destination address. And just to show you this a little bit more, you can see here's the data. So there's the full header, and then here's your data. But believe it or not, some of this data is the header of the previous layer. So that's quite important, is that in terms of IP version 4 or the layer 3, it'll just see this section here. And I wonder if I can bring up let's see if we can, I don't have it. Okay, so in terms of layer 3, it's only going to look at this. That's network layer header. And then the rest of the bits here will just be termed data. But believe it or not, some of these bytes are the headers of the previous fields. Do you remember that remember earlier I showed you that as the data goes down the stack, it keeps getting headers put on. So what you'll find is as follows. There's the data, then there's the transport layer header. Then it gets put to the network layer. Then there's the network layer header, but it sees all of this as data. but really this section here is still header. And then when it goes down to the Ethernet layer, layer 2, then Ethernet layer will put its header and see all of this as data. But really we know that this would be the place where we could find the network layer header, and over here is the place where we could find the transport layer header. So that's why Wireshark is able to look inside and see all these little headers. You see, there's layer 2 header, there's layer 3 header, and there's layer 4 headers. Alright, so let's move on. Right, so now we are looking at how we subdivide our networks. Now here you see a very large network, and these large networks start to become quite resource hungry. For example, remember that in order for these devices to be connected to each other, there's a lot of signaling information, a lot of broadcast. What's a broadcast? If you look at your Wireshark, you could see here, let's not do TCP, let's look at an ARP. And an ARP is often a broadcast protocol. You can see there it says broadcast, and you can see what it's happening is, if you look at its sending address, you see destination, there's the source, sorry, the source is me, but look at the destination. The destination is all F's, telling me that it's being sent to everyone on this layer 2 network. So that means that it starts looking for a lot of replies, and by doing that, it actually loads the network. So sometimes it's better to separate networks. Now we ask ourselves, how do we want to separate the network? Do we want to separate it in terms of geography? Like one part of the building may be called one network, and another part of the building they're calling this east office, and another part north office. But the problem arises is, as you can see, there's an HR person, and there's an HR person, and there's an HR person. They all want to have access to HR resources. And here you've got a salesperson. A salesperson should not be able to see the same resources that the HR person sees. So even though we've subdivided the network using geographic location, we have not solved the problem in terms of who can see which resources. So here we find sales can see the legal resources and the HR resources, so that's not really going to help. Now, what we could do is also divide it in terms of purpose. All the HR people on the same network connected to the same servers, while the sales people on their network connected to their servers, and then legal and so forth. So that does help quite a lot, because now we can almost secure the network in terms of who can see what and who's got access to which resources. Now, one of the benefits of separating networks into purpose is that here we've got a sales office. The sales office needs very high reliability and good network speed, but they might not require high bandwidth, for example. Here you might have a group of people who are doing maybe multimedia projects. Maybe they're an art department. Maybe they're doing graphic design. Now they would need high bandwidth, and they're probably using similar software. So it's also easier to provide these similarly set up devices to have access to which will probably also use the similar resources. So that's why it makes sense to separate networks in terms of purpose, because they probably use the similar software, they probably do the similar bandwidth footprint, and so forth. So as the networks grow, we become forced to subdivide them. Now here we've got a switch, here we've got a switch, and they're connecting all these networks together, giving everybody access. Now, something that people don't realize is that there is a theoretical and a practical limit to the amount of hosts we can add to a network. For example, all of these hosts can see all of the other hosts on this layer 2 network. For example, you might have 500 hosts here, all of them sending their status updates and everything, but all 500 hosts should know the addresses of all the other hosts on the network. And this huge addressing requirement starts to load up the network quite a bit. And it might be better to start subdividing it by using a router. What happens here is that you might have this network, but all this signaling information is blocked by the router because the router does not forward a broadcast. So any broadcasts are lost here or die here at this router. And all the broadcasts on this network die here at this router. So the broadcasts here do not forward into this network, and the broadcasts here do not forward into this network. So that helps us subdivide networks. So if you look at the earlier version, you'll see that each one of these devices has to know the address of each of the other devices on this single broadcast domain, because they can each communicate with each other. So here we see that there is an entire broadcast domain here, because all of these computers can effectively connect to each other. They can communicate with each other. And as we separate these two domains, we can now provide different IP addresses, and therefore all the devices are connected but are no longer local. This is a local network, this is a local network, but this network is not local to this network. These people cannot see what these people are doing unless they are the router allows the communication. But remember, then it is 1-to-1. That is called unicast. So all the broadcasts are lost. When this guy is looking for an IP address, nobody on this side cares. When this guy is sending out an error, say an ICMP packet, nobody here cares and nobody here will even know about it. So the router will only relay the information that is for a specific host on the other network, thereby greatly reducing a lot of unnecessary communication. And then what it also does is it also helps with the security. For example, people on this network here, they will be able to get access to their resources. As you can see, these people are connected to these servers, and there they have access to their little resource centers there. But when we're going across the network, you can see via the routers, well, these servers are hidden behind this router, and their IP addresses are not advertised, and their location therefore is almost hidden. So unless you are given access, you will not be able to just have access to these servers, because the router will block that. You won't even see that these servers are available. You won't even see their IP addresses. The router will block it. All right. Now, as we move on, we see that we come to the point of the gateway. What is a gateway? Well, let me ask you something. If you want to get out of a network, or if you want to get out of let's start with a room. Let's call this a gate in a room. You can see that in any house, now I bring up Minecraft. Here we have somebody's very nice house here. And can we see there's a gateway. How do you get into this house? You have to go via this gate. And how do you leave? If you're living here in this house, how do you get out? You've got to go through this gate. So this is called a gateway. And that's what I want you to think about when you think about a router. There is a router, often called a gateway. Even when you look at your networking information, if you go to network and internet settings, you will see here adapter settings, and you will also see here gateway. There we go. Default gateway. What it's asking you is, what is the address of the router? That is the gateway's address, or the router's address is the gateway, or they're one and the same thing. And what it's asking you is, if I cannot find the person you're looking for on this local network, where do I forward the packet to? Well, I forward it to the gateway. Let me say that one more time. Extremely important. If I cannot find the person or the bedroom in this house, and you've got an address, and the address happens to be nobody in this property, well, I have to leave the property. I have to go out the gate. So if you're trying to send some a parcel to somebody in a different state, well, guess what? You've got to get out of this gate. And that's how the router works. Here I have a host. The host has an address for everyone on this network. And it also has its own address. But it wants to send a packet to someone who's not on this network. The switch does not even have that IP address listed in its switch access table. So what happens? The packet automatically gets forwarded to the gateway. So when the IP address does not belong to this network, it gets sent to the router for the router to decide what to do. Hosts do not know how to deliver data to devices in a remote network. This is the role of the gateway. So even though this guy has the IP address of the remote client or the remote person he's trying to connect to, he does not know how to get there. He just forwards it to the gateway. And the address for this destination is unknown, so packets are passed to the gateway router. And it works on this hierarchical basis. In the same way I started this lecture explaining the addressing system. If you want to send a letter to someone and their full address is Jane Doe, 170 West Tasman Drive, San Jose, California, USA. The first thing we're going to look at is it even on our local network? Is it even in our local country? Yes. Well, then we know. Now we look at the state, the city, the road or street or avenue, and then the house number. So this is a hierarchical addressing system, which is similarly shown in this IP address. Can you see that each one of these octets, this is an IP address consisting of 32 bits. Each one of these octets has information. It tells the router something. For example, if you are 192.168.18.57 and the person next to you on their device is 192.168.18.58, well, you'll be able to communicate with each other because you are literally on the same network. But if you are 192.168.18.57 and you are trying to send a packet to 192.167.18.56, guess what? You're on a different network. It'll have to forward it to a router to deal with. So this is what we look at when we compare the postal addressing system with the IP version addressing system. These octets can also be looked at as, and I'm going to use this quite loosely, kind of like house number, street, city, country, if you like. Do you get what I'm saying? So house number, it's usually quite local. If you're 57 and somebody else is 56, they're probably very close to you. They're on the same LAN, local area network, especially if all of these are the same. And if you are both 192.168 and you're both you're 17 and someone's 18, well, they're probably still maybe not very far away from you, but they might be quite maybe one hop away from you. All right. So we will discuss this in more detail when I do IP addressing, but I just wanted to plant that seed so you get an idea of how the IP addressing can also be seen hierarchically. All right, now we're going to look at how gateways enable communications between networks. Now this guy here wants to send a packet. Now he is 192.168.2.30. It says here, I only know the addresses of the devices on my network. You see, once people connect to the network, they share each other's addresses. Did you see here when I showed you these ARP packets here? Can you see that they all are on the layer 2 and they are literally sharing addresses? They are saying, who has this address? Tell this person. Who has this address? So they're literally identifying people on networks. And what happens is all these devices eventually get to know all the other devices on the network. And the switch has a switch MAC address table, which it also populates, also knowing who to forward packets to. But if you look over here, we've got a 192.168.3.4. So this is a different IP address, and here we've got a gateway, and here we've got a gateway. Now, if this person here wants to send a message to someone who's not on this network, guess what? Goes to the gateway, the router. The router checks the IP address and says, okay, do I have a nearby route or a nearby connection where I can forward this packet to? Yes, I do. Forward it to gateway 19, forward it to this router. And then this router will then look and say, yes, I have someone with the 192.168.3.4 address on my local network. Boom, and it'll forward the packet to that person. So now I'm going to go through this step by step with actual IP addresses that have been assigned. Right, so let's start. This person here with address 192.168.2.30 is ready to send a packet. He says, is this packet destined for a device on this network? No. It is destined for device 192.168.5.6. Look at this network. This is called network 192.168.2.0. He's looking for someone on 192.168.5. This is 2. This is a totally different network. Nobody with this IP address is on this network. So what happens? He's got to forward the packet to the router. The packet finds its way to the gateway. So just to highlight to you, we are trying to get a message to this person here, 192.168.5.6. This is the host's IP address. They are on the 192.168.5.0 network. Their number on that network is 192.168.5.6. Think of it like a street. They are on this network, 192.168.5.0 network. There are many people who are on this network. This happens to be the 192.168.5.0 network, or the street called 192.168.5. There are many people who are on that street. He happens to be house number 6. You see, he's 192.168.5. He's on the same street, but he's house 6. You might find somebody else here is house 4 and somebody else house 3. You get what I'm saying? I'm just using a metaphor to explain that. All right. So 192.168.5.6 is the host we are trying to get to. He's not on the same network where the 192.168.2.30 person is trying to send a message. See, this person here, his IP address of the source, 192.168.2.30. He is currently residing on the 192.168.2.0 network. Think of it like a street. It's like he's on the 192.168.2 street. And on that street, there are many people who live there. He just happens to be house number 30 who's living on this street, the 192.168.2 street. All right, so he wants to send a message to his colleague over here who happens to be number 6 on the 192.168.5 network. All right, I hope you got that. Now, because the 5.6 is not on the 2.3 network, this is a different network. It's in a completely different subnet. We've got to forward the packet. Boom. There goes the packet to the switch. The packet is sent to the gateway. The switch realizes that he does not have this IP address in his switch MAC address table, the IP table, and he forwards it to the router. The router says, okay, do I have someone connected to me on my local networks that has 192.168.5.6 IP address? No, this router does have a direct connection, but look, the direct connection is 192.168.3.0. So he does not have a direct connection, which means he's not going to allow the packet to go internal. He's going to forward the packet on to the next hop. It is not a directly connected device. He's going to now forward it on. Boom. Sends it to this router. This router then says, is this packet destined for a directly connected device? That means, do I have a device connected directly to me? He's saying, the router is saying, is this host plugged into my interface? No, he's not. So this router then says, all right, I will forward the packet. Now he forwards it to this router. This router says, is this packet destined for a directly connected device? He's asking, Do I have a device that is connected directly to me with 192.168.5.6 address? Yes, it does. The switch is just a relay station. So even though it is not directly, literally plugged into the router, it is plugged into the switch, which means it is shared. It is one, you can call it one domain. So the 192.168.5.6 is on this network, which is directly connected to this router. So guess what? The router just forwards it to the switch, and the switch forwards it to the final receiver, the host with the number 6 IP address. So the IP address arrives at this destination, and the IP header is removed. The TCP segment is passed to layer 4 on the device, and they have confirmed a connection was established. Remember, the TCP is in charge of whether the connection was established, not the IP, the network layer. All right, so there you can see how we, using a hierarchical model, you see this happens to be 3 network, 4 network, and then finally the 5 network, how we forwarded the packets, routing it, briefly described here. Right, looking at this picture here, we can see a few hosts on a local network. Now, what I want to draw your attention to is that each host has a unique IP address. Look, this one is 192.168.1.3, 192.168.1.2, 192.168.1.1. So these 3 hosts each have a unique IP address. But what do you notice that they have in common? They each have the same gateway. Now, earlier I showed you how to set the IP addresses. You in the Windows stack here, you would put your IP address and then your subnet mask, and here's the default gateway. Now the default gateway is the device that allows you to exit the network. Now, can you see that I have 3 hosts or 3 devices connected to this network, and each one of these devices needs a way to exit the network. If they need to connect to somebody outside of the network, they each need to have the same gateway. Can you see there is only one gateway? And the gateway, or the router's IP address, the router's internal IP address is 192.168.1.254. And that is the gateway address of each one of these hosts. Can you see 192.168.1.254? Now, earlier I showed you a gate here. Now, if you are staying in this top bedroom here and you need to get in onto the main road, or you need to go to the shops, you will walk down the stairs, come here and through the gate. If you are staying in this bedroom here, you will still walk down the stairs, blah, 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 and come through the gate. Can you see that no matter where you came from on this property, to exit the property, you still have to come through the same gateway? So that is why each one of these hosts or devices on this network have the same gateway address. It's the address or location of the device that allows you to access another network or to exit the network, and that happens to be the router's internal IP address. And I've just showed you that that's where you would put the properties. So you can see there's the IP address, your unique IP address, and there's the router's internal IP address, or as we call it, the default gateway. Right, now having a look at the little routing table here, when you are on a network and you are trying to access another network, then the router has next hop addresses. For example, if you look at this little routing table here, it shows you destination network 10.1.1.0/24. And if you want to go to the 10.1.1.0/24 network, you have to go through the 192.168.1.2/24 network. Can you see how it's telling you? If you're looking for this, you need to go there. So here we go. If you are looking for this address, 10.1.1.0/24, you need to find the interface that has address 192.168.1.2. Can you see that? So if you're sitting here and you're looking for this address, the router knows, okay, forward the packet to this router, the router with this address, because it has the network connected to it called 10.1.1.0. So that's just showing you how the forwarding system works. Now, if you had to log in to the router itself, this is what it would look like. 10110. Go, if you want to connect to this network, root, go via 192.168.2.0. And which interface? Fast Ethernet 0.0. That's it. That's how simple it is. And this is the routing table. If you say show IP route, where would you do this? Well, you could go to Packet Tracer, and you would put a router here. And once you've configured your network, when you've logged in, you could go, you'll just wait for it to boot up, and then you would type the command show IP route. Right, I have this picture here showing route entries, and what happens is I want to show you the layer 2 and the IP headers, and what happens when the datagram or the frame enters the router. So what happens is, step 1, the router removes the layer 2 encapsulation. Remember that the data comes to the router as a frame or as bits, but it first has to be understood in terms of layer 2. Now, we haven't done layer 2 yet, so what you need to know is that that's the MAC addressing information, and there are other protocols that exist in layer 2. But the router's not that interested in layer 2. It's interested in layer 3. Remember when I started this video, I kept saying that this is the layer of routing. Layer 3 is the layer of routing. So what it does is it has to decapsulate. It removes the layer 2 encapsulation. So there's the layer 2 encapsulation. It removes it to view only the IP information. So it now extracts the destination IP address. So it finds that IP address, which is part of the layer 3 information. It then checks its routing table for a match. In this case, we're looking for 10.1.2.0, and we're seeing if that is available in the routing table. What is the next hop for us to get to the network 10.1.2.0? So we go to the next step. Network 10.1.2.0 is found in the routing table. It means that it's already been configured, and that if you're looking for route 10.1.2.0, you go via a certain other network. So there's a match. The router can deal with this packet. Now we go to step 5. The router then re-encapsulates the packet. Remember, it's still going out. Maybe it's still leaving the router via layer 2. Layer 2 protocols are still at play here. So it has to re-encapsulate it, put the MAC addresses and other logic link control protocols are at play here. It has to re-encapsulate, as you can see there, the layer 2 protocol. And now it's ready to be sent to the next hop. Now, what happens if there is no next hop address in the routing tables? For example, here we go. A packet arrives, a frame arrives at the router, and the router will do the same thing. It will remove the layer 2 information, so it will decapsulate, and now what will happen is it's looking for information, it's looking for a route for 172.16.2.0. So we got to extract the IP address that we're looking for. We're looking for a route for 172.16.2.0. And what happens is the router checks for this IP address, and it hasn't got it. It doesn't have that. So what it does is it sends it to its what we call the gateway of last resort. It's the router's gateway. So there we go. Network 172.16.2.0 is not in the routing table. So the router is also set to have a default route. It then forwards it to its default route or its default gateway, which happens to be 192.168.1.2, which has already been configured in the router. And therefore it re-encapsulates the packet back with the layer 2 information, and there goes the frame out to the gateway of last resort. Finally, what happens if there's no route entry and also no default route? Well, what will happen is the the frame will land at the router will de-encapsulate it, look at the IP address and see, I don't have a root and I don't have a gateway of last return. Right, bin it. So it means it drops it, the packet dies. IP does not have a method of telling this sender that there was a problem. Other protocols do. There are other protocols to send signaling information, error messages, which I have videos on, which is to do with the ICMP reporting. But in terms of layer 3 routing, no. IP does not have a function to tell you that the packet was not received and the packet was dropped. And one of the reasons why is because it would add more overhead, and adding more overhead would slow down the communications. Now, I'll just go through this very briefly, because this is bringing us to the end of the video, and that is static versus dynamic routing. Static routing just means that you've got to manually set all your routing tables, while dynamic means it's done via various routing protocols. And what happens is the routers send status updates to each other advertising their routes, and this changes moment to moment. So this is what is the most common protocol specifically on the internet. But maybe in your small office, home office, you might use static routing, where you just set it up manually because the routes don't change. Alright, so that brings me to the end of the video, and I would like to just say thanks for watching.